Hello, everybody. Welcome back. Today we are going to be talking about rates of change. So there's two types of rates of change. Recall that we have our average rate of change, which finds the average velocity, right, or the average rate of change between two separate points. And we also have our instantaneous velocity or instantaneous rate of change, which has to do with the slope of the tangent line, right? Because the slope of the tangent line, right, tangent line, the slope of it shows us what the rate of change is at that particular point, right? So the main difference here, if we're thinking about it one way, is for an instantaneous rate of change, we're only measuring the rate of change or velocity at one singular point. For the average rate of change, it must be the average amongst a certain number of things, right? The average between two different points. So let's go ahead and do that with this example. Just a reminder, in this example, I will be using first principles as we have not done derivatives yet. But yes, there is another faster way to calculate the velocity using the derivative method, which I will not be sharing today. Okay, so example one says that a pebble is dropped from a cliff 80 meters high. After t seconds, the height s in meters of the pebble is represented by this equation. S of t is equal to 80 minus 5t squared from 0 to 4 seconds. So the first question asks, calculate the average velocity of the pebble between t equals 1 and t equals 3 seconds. So this, as just a reminder, it's going to be s of 3 minus s of 1 over 3 minus 1, right? We want to find the average, the change in y over the change in x, right? This goes back to the very simple definition of our slope back from grade 9, right? That slope is delta y, right? Or change in y over change in x, which is equal to s of 3 minus s of 1, right? So the y values at those points, or the outputs of our function, and then over the change in the inputs of our function. So let's figure out what that is. Well, 3 minus 1, that's obvious. That's just going to be 2. But what about s of 3 and s of 1? Let's calculate those on the side. S of 3 is equal to 80 minus 5t squared. So that's 80 minus 45, which is 35. So the answer here is 35 minus s of 1. Well, s of 1 is 80 minus 5, 1 squared, which is 80 minus 5, which is 75. So our answer looks like we're going to get negative, is it 40 here? Yeah, negative 40 over 2, which is negative 20. Okay, so that means that after t seconds, the velocity, right, the average velocity between 1 second and 3 seconds is negative 20 meters per second. Now, why did we get a negative answer? Because it's going down, right? We're not going upwards or forwards, we're going downwards. And so the average velocity, therefore, is going to be negative to indicate that we're going down. Okay, let's try the next one here. Calculate the average velocity of the pebble between t equals 0.5 and t equals 1 second. So we want to know what's the average from the time we're at half a second and 1 second. So let's see. Let's see if it's faster or slower than the one above. Now, given that this is a quadratic, some of you might already be saying, oh, obviously, it's going to be this way, but let's actually go ahead and solve it and see what it is. So again, we want to find our slope of the secant line, which is delta y over delta x, which is s of 1 minus s of 0.5 divided by 1 minus 0.5. So we already calculated that s of 1 is 75, and we already know that 1 minus 0.5 is just going to be 0.5. So we just have to find s of 0.5, which is going to be 80 minus 5, 0.5 squared. So 0.5 squared is 0.25, right? And let's see, what's 5 times 0.25? is going to be 1.25. So 80 minus 1.25 is 78.75. So let's see, 78.75, 75 divided by 0.5 gives us negative 7.5 meters per second, right? And of course, it's going to be, a bit of a slower drop in the beginning, right? If we think about how a quadratic opening down is going to work, that's of course going to be the case for us. Okay. Let's calculate the velocity of the pebble at t equals 1 second. So just a reminder, we're going to use the first principles method, but yes, there are other valid methods to solving this question as well that I won't list just yet. So to figure this out, we need to find the slope of the tangent line, which is going to be the limit as h approaches 0, f of x plus h minus f of x over h. Or I guess in this case, s of t plus h. I'll switch around the equation to get the variables correct. It should really be s of t plus h minus s of t. Okay, so this is going to be equal to the limit as, let's see, limit h approaches to 0, 80 minus 5, and then instead of t squared, it would be t plus h squared, and then minus s of t, so minus 80 minus 5t squared all over h. Okay, and now I'm going to expand and simplify this. So here we would have limit as h approaches to 0, 80 minus 5, let's see, t squared plus 2th plus h squared minus 80 plus 5t squared all over h. That's going to be equal to 80 minus 5t squared minus 10th minus 5h squared minus 80 plus 5t squared. Okay, so 80 minus 80, that's going to give us 0. So we're going to cancel those out. Minus 5t squared plus 5t squared, let's cancel those out. And then we can actually cancel this h out with one of the h's here and this h here since it's all that's left. And then we can also plug in our h equals to 0 right now. So we can say if h is equal to 0, then the answer is negative 10t. That is all that is left here, right? Because minus 5h just becomes 0 because then h is still involved in there. So the answer is negative 10t. And given what we got for these answers here, that makes good sense, right? It's right in the middle. It's between those two values, right? It's between the value, which is the average from 0.5 to 1 second, and the value from 1 second to 3 seconds, right? D asks, what can you conclude about the velocity of the pebble as it falls? And what we can conclude is that the pebble falls at a faster and faster rate the further down it gets, right? At first, it's only falling on average minus 7.5 meters per second, then minus 10t, right? Which if the time is 1 second, right, would just be negative 10, right? Negative 10 meters per second, right? Because t is 1. And then after that, it's falling minus 20 on average from 1 to 3 seconds. So it's falling faster and faster downwards as time goes on. And that's the main conclusion that we can get here. All right, let's try 2 more examples of this. The next one says a toy rocket is launched straight up into the air such that the height s in meters at time t in seconds is represented by s of t equals negative 5t squared plus 30t plus 2. What is the velocity of the rocket at 2 seconds? So this one's very similar to part C of our example 1. So I encourage you to pause this, write down the question, and give it a try on your own, and then we'll take it up when you're ready. Okay. So what is our rate of change? Well, the rate of change or the velocity, is the slope of the tangent line, right? And the slope of the tangent line is the limit as h approaches 0, s of t plus h minus s of t all over h. That is the same as the limit as h approaches to 0, 5t squared, right? T plus h squared plus 30t plus h plus 2, and then minus 5t squared plus 30t plus 2 all over h. And now we've got to expand and simplify. This is the not so fun part, but in a second, a whole bunch of stuff is going to cancel out, which is good. Limit as h approaches 0 is going to be 5t squared plus 2th plus h squared plus 30t plus 30h plus 2 plus 5t squared minus 30t minus 2 all over h. And then let's do one more expansion of those first brackets that I didn't quite get to. This is going to be 5t squared plus 10th plus 5h squared. And then plus all the other stuff, plus 30t plus 30h plus 2 plus 5t minus 30t minus 2 all over h. And let's not forget our limit as h approaches to 0. Now let's cancel stuff out. So let's see. What cancels out here? This should have been 5t squared. And that is the first thing that cancels out, the 5t. And then, oh no, that does not cancel out actually. Okay, well, what does? What does? Let's see here. Well, we have minus 2 and plus 2. Those cancel out, right? Oh, and wait here. This should have been, I made a mistake here. This should have been negative 5 from the beginning. So actually, I'm just going to swap that out a little bit. These should all be negatives. Okay, I knew there was some mistake there. Okay, all cleared up. All right, so then this negative 5t squared with this positive 5t squared, those cancel out. Then we have negative 30t plus 30t, so those cancel out. And then we can cancel, now everything just has an h left, so we can cancel this h out with this h, one of these h's, and this h here. And then when we plug in h equals 0, we're left with negative 10t plus 30. Yeah, that's what we're left with. Negative 10t plus 30. Now it asked, what is the volume when the rocket is at t equals 2 seconds? So when t equals 2, it is negative 10 times 2 plus 30 is equal to negative 20 plus 30, which is equal to 10. So therefore, the velocity at t equals 2 is 10 meters per second. Very good. All right. Let's try number 3. Number 3 is fairly similar, but a little bit different. But I still encourage you to try this one before we go ahead and do it as a group. So this one says a medicine is administered to a patient. The amount M of the medicine in milligrams in 1 milliliter of the patient's blood, T hours after injection, is given by this equation. Find the amount of medicine in a patient 1 hour after injection, and find the rate of change of the amount M after 1 hour of injection. So to find the amount of medicine in the patient 1 hour after injection is very simple. All we need to do is plug 1 in for M, right? And find M of 1, because again, T represents the number of hours after the injection is given, and we want to find out how much medicine, which is M of T, right? The amount of medicine after the 1 hour. So here we just need to find M of 1, which is equal to 1 minus 0.331 squared, which is equal to 1 minus 0.33, which is 0.67, okay? So that means 0.67 milligrams is the amount in the patient after 1 hour of injection. Now they want to know what is the rate of change of the amount of m 1 hour after the injection. So here we want the slope of the tangent line, and then we need to plug in t is equal to 1 to find out where is it at 1 hour after the injection. So let's do that. So we know that the slope is going to be limit as h approaches 0, m of t plus h minus m of t over h. And that is equal to t, right, which is t plus h minus 0.33 t squared, so t plus h squared, minus m of t minus t plus 0.33 t squared all over h. Oh, and I forgot, limit as h approaches to 0. We can't forget that. Okay. All right, so then here we would have t plus h minus 0.33 times t squared plus 2th plus h squared. Let's see, and then minus t plus 0.33 t squared. And actually, I normally wouldn't do this, but I am going to cancel out this minus t and this plus t because I can already see those are going to cancel. Okay, so the next one is just going to say h minus 0.33 t squared plus, let's see, 0.33 times 2, so that's going to be negative 0.66 th minus 0.33 h squared plus 0.33 t squared. All right, so those are going to cancel. And now we're left with h's. So this h cancels here, 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 and here. And what are we left with? We are left with limit as h approaches to 0, 1 minus 0.66 t minus 0.33 h. So let's see, what is that? That is going to be, if we plug in 0 for h, we're going to get 1 minus 0.66 t. And t is 2, or no, t is 1 in this case. So when t is 1, we're going to get 0.33. Good. And you may have gotten, if you quite literally do this, you'll actually get 0.34, but we had some rounding error in there. I'm not going to worry too much about that though. So yeah, 0.33, or I guess, you know what, 0.34 works as well. Let's go with 0.34 actually. I think that's going to be better. Okay, so therefore the rate of change would be 0.34 milligrams per second at that 1 hour mark. Or sorry, milligrams per hour rather. Time was in hours, so my apologies. Make sure to get the units right, unlike me over here apparently. All right, well, there we go. All right, well, that is it. That is everything for this first one. Next time we will be talking about limits.